All right, okay, so last week we discussed about this maximum matching problem in bipolar graphs. Okay, so in this problem we're given a bipolar graph. Okay, so in a bipolar graph you can divide the vertex set into two sets. Here we call them x and y, so that all the edges in the bipolar graph are between x and y. Okay, so this is bipolar graph. And we consider a problem of finding the largest matching. So here matching is just a set of edges, okay, such that these edges do not share endpoints or they do not touch each other. Okay, so that's a matching, and we want to have the largest matching. By largest, I mean the most edges, okay, in a matching. So for example, in this bipolar graph, we can have at most two edges in the matching. So this is really the maximum matching. Okay. So we want to have an algorithm to find the maximum matching. So the basic idea of the algorithm that we discussed last week is that we're going to start with just any matching. Okay, perhaps the maximal matching. So here, maximal matching is just a matching where you cannot add any more edges, because when you add any more edges to it, then you're going to have some edges that share endpoints. Okay, so this one. So this is a maximal matching because for these three vertical edges, you cannot add any one of them to this matching. Otherwise, you will create edges that share endpoints. Okay. So given this maximal matching, we want to find a way to create a larger matching. And the idea we had is that we want to have a spatial path. So in this path is, first of all, it alternates between edges in your original matching and edges not in your original matching. So like this one, so the first edge is not in the matching, the second one is in the matching, and so on. Okay, so it's alternating. And then you have to make sure that in this spatial path, the two endpoints are not saturated, because that by saturated I mean matched. Okay, so this vertex is not incident to any one of these green edges. So this one is not saturated. Similarly here for this one, it is not saturated. Okay. So after you find this alternating path where both endpoints are not saturated, this is when we call that it is an augmenting path. Okay, because we can use it to find a larger matching. Okay. So we can take the exclusive OR of the edge sets between the edge set of this path and the edge set of the matching. Okay, and then we can get a larger matching. Okay. All right. So the basic idea is just to find augmenting path. Okay. So we studied three questions related to augmenting path. First is the existence of M augmenting path. Okay, so M augmenting path means that the matching that we are considering is M, and we want to find an augmenting path for M. Okay, so that's M augmenting path. So given a matching M, we want to know whether can we find an M augmenting path. Okay, does it exist? Okay. So the result is that if the matching we have is not the best, okay, if it is not the maximum matching, then there's always an M augmenting path, okay? So that's a good news, okay? So because when the matching is not the largest, we want to use this method to find the larger matching. So we want to make sure that whenever the matching is not the largest, there's always an M augmenting path. All right, so the second question is to find it, okay? So if we know that there must be some augmenting path, we want to have an algorithm to output the augmenting path, okay? And the algorithm we have so it gradually extends M alternating path. Okay, so it's easy to find alternating path, right? Because you just alternate edges. Okay? First edge is not in the matching, second one in the matching, and so on. So it's easy to find alternating path, but it's not that easy to find augmenting path, because the difference is that in an M augmenting path, you have to make sure that the two endpoints are not saturated. Okay, so that's somewhat challenging, and we want to find an algorithm to find M augmenting path. So in our algorithm, we start with unsaturated vertices, because the two endpoints must be unsaturated. So we're going to start from the set of unsaturated vertices in X. Okay, so this set U, this is just the vertices in X that are not saturated by the matching M. Okay, and then we're going to maintain two sets, and these two sets will be used in today's proofs. Okay, so the first set is S. Okay, so S is a subset of X. Okay, such that you can reach these vertices in S by an M alternating path starting from the set U. Okay, and T is defined similarly. The only difference is that T is a subset of Y. Okay, so if you can reach this vertex using alternating path and it is in Y, then this vertex is in T. Okay, and yeah, so the way we find the M augmenting path is just to construct these two sets S and T. Okay, so first of all, we're going to divide the algorithm into rounds. So there are multiple rounds in the algorithm. So in every round, we're going to pick a vertex in S, and then we're going to first go down. Okay, so when we go down, we must use edges not in the matching. Okay. So for example, when we pick this vertex W, and when we go down, we're going to use edges not in the matching. So we can use these two black edges, okay? And then we're going up, okay? So actually there are two cases here. So the first case is that when you go down and you reach a vertex in Y that is not saturated, then this means you have found an M augmenting path, right? So we start from some unsaturated vertex in X, and then blah, blah, blah. Then we go to an unsaturated vertex in Y, which means we have found an M augmenting path, okay? So in that case, we can just output the augmenting path. And the other case is when we go down, the vertex is saturated. So in this case, we can then go up using the edges in the matching, okay? So whenever we reach a vertex, we'll put them into S or T, depending on whether it is in X or in Y. Okay. Okay, so this is an example. So in this bipolar graph, we have this green matching. Okay, we want to find an M augmenting path. And we first find the set of unsaturated vertices in X, that is this guy, okay? So for this input, the set U only consists of one vertex, this vertex V. So initially, S only contains this vertex V, okay? And then in every round, we just first go down using edges not in the matching. So we use this black edge to reach this vertex. So we're going to add this vertex to T and then go up, okay? The reason that we go up is that this one is saturated, which means this vertex must be instant to some edge in the matching. In other words, it is saturated, okay? So after we go up, we can add a new vertex to the set S, okay? So in every round, we just repeat this process, okay? Find a vertex in S and go down using edges not in the matching, and go up Okay, so eventually you're going to see either the algorithm finds a vertex that is not saturated, like this one, okay? In which case, we have an augmenting path, okay? And in other cases, after you check all the vertices in S, you may find out that actually there are no augmenting path. So this means that all the vertices in T are saturated, okay? And there's no unsaturated vertices in Y. So in this case, the algorithm just output no, there's no augmenting path, okay? So this brings us to the final question, okay? The final question is, what if the algorithm does not output any augmenting path? Is there a way to show that the algorithm is correct? In other words, the matching is the largest possible, so there's no augmenting path, okay? So today we're going to answer this question, okay? But before that, there's a useful property about S and T. Okay. So the useful property that we're going to use later is that let's consider this one. Okay. In this case, okay, this vertex is also in U. It's also in T, sorry. Okay. So the property I'm going to mention is that T, the set T, is actually the set of neighbors of S. Okay. So all the neighbors of S are in T, okay? And T contains all the neighbors of S, okay? So in other words, if you have a vertex, and this vertex is adjacent to some vertex in S, then that vertex must be in T. Because when we run this algorithm and say we have another vertex here, okay, then when we consider this vertex V, when we go down, we're going to add this vertex to T, okay? So yeah, every neighbor of vertices in S must be in T. Okay. Right, okay, so to answer the final question, that is, when the algorithm cannot output any augmenting path, we want to have a proof, a certificate to show that the matching we have is already the best, okay? So the basic idea is to find an upper bound. So maximum matching problem is a maximization problem, okay? We want to maximize the number of edges in the matching. So in this maximization problem, we want to find an upper bound, okay? So when our solution meets this upper bound, which means they are equal, this means this is actually the best because it already meets the upper bound, okay? So we want to find an upper bound for the size of maximum matching. So the upper bound that we're going to consider is a minimization problem called vertex cover, okay? So vertex cover, in vertex cover, you want to pick vertices to cover edges. And it is very easy to cover an edge. To cover an edge, you just choose one of its two endpoints, okay? So for example, to cover this yellow edge, you can use this vertex or this vertex, okay? And in this particular example, we already know that the size of the maximum matching is 2, okay, because you can pick at most 2 edges, okay? And to cover all these edges, okay, when we consider vertex cover, when we want to cover all the edges, we can just choose these two vertices. Okay? So once you have these two vertices, you can cover all the edges. Okay? So from this particular example, you can see that the size of this vertex cover is equal to the size of the maximum matching. Okay? So I only mentioned that this is a vertex cover. Okay? By choosing these two vertices, you have a vertex cover. But it's easy to see that this is actually the minimum, the best vertex cover, the smallest vertex cover, because you cannot choose just one vertex to cover all these edges. Okay? So to cover all these edges, you have to use at least two. Okay? And since we have a way of picking just two vertices to cover all these edges, we know that these two green vertices, they form a minimum vertex cover. Okay? So in this case, the size of the minimum vertex cover is equal to the size of the maximum matching. Okay. So in general, if you have any matching, okay, and you have any vertex cover, okay, then the size of the vertex cover will be an upper bound for the matching. And why? The reason is that, say you have a matching here. Okay, so the key property is that edges in the matching, they do not share endpoints. So if you want to just cover the edges in the matching, let's forget about all the edges in the graph. Let's focus on the edges in the matching, just to cover these edges in the matching. Since these edges in the matching, they do not share endpoints. So if you have, say, 5 edges in the matching, then you have to use at least 5 vertices to cover these edges because they do not share endpoints. So that you cannot use one vertex to cover multiple edges. Okay? So that's the key property. So so that's basically the proof. Okay? 所以刚刚讲的蛮重要的一点就是，如果是 matching 的话，这些 matching 的 edge 不会共用端点。所以如果你今天 edge， 比如说 matching 有10个 edge， 这10个 edge 一定就是有点像独立的，它们不会碰在一起。所以你光要 cover 这10个 matching 里面的 edge， 就你忘掉说什么刚刚要 cover 所有 edge 不需要。我们今天把问题变简单一点，你只需要 cover matching 里面的 edge 就可以了。光这样子，你就已经要10个 vertex， 因为这些 edge 都没有共用端点。所以 vertex cover 任何一个 vertex cover， 它的大小一定至少就会是 matching 的大小。OK， 所以到这边有问题吗？稍微复习一下我们上礼拜讲的内容。Okay, so today we're going to also show that this is actually a byproduct of the third question that we're going to consider. That if the graph is a bipolar graph, then actually the size of the minimum vertex cover is equal to the size of the size of the minimum vertex cover is actually equal to the size of the maximum matching. Okay, so we're going to prove this as a byproduct of the answer to the third question. Okay. And also I had a remark last week that if the graph is not a bipolar graph, then this equality no longer holds, okay? Because if the graph is not bipolar, we discussed last week that it must have some arc cycle, okay? So in an arc cycle like this one, this is C5, the maximum matching has 2 edges, okay? This is the best, you cannot have 3 edges in C5. And the minimum vertex cover is 3, okay? So you cannot use just 2 vertices or less to cover all the edges in a C5. Okay? So in this case, these 2 values are not the same. Okay. Okay. So next we're going to consider the third question. Okay. So the context is that okay, so this is the background. Okay, the algorithm cannot output an M augmenting path, and the goal is to find a vertex cover. Let's call it C, such that the size of the vertex cover equals the size of the matching. Okay, so this is our goal. So once we have this vertex cover, it solves the last question. So why? So what happens if we have this vertex cover C? I claim that once you have this vertex cover, it is sort of a certificate to show that the matching M is the largest possible. So can you see why? Okay, so first of all, we already know that every matching has a size of, at most, the size of C. Why? Because we said that C is a vertex cover, and the size of the vertex cover is an upper bound for the size of the matching. So every matching has at most like C edges. And since now you have a matching, this matching, whose size is exactly C, which means this matching is the best possible. 所以这边我们刚刚前面已经说，就是 C 就是任何一个 verse cover，它就是一个它的大小就是 matching 的上限 ，OK， 最多就是跟 verse cover 的大小是一样大的。那这个就是我们前面已经讲过了，这里 OK， 因为你光要 cover matching 的 size， 你就需要那么多个 vertex 才可以 cover， 所以 C 的大小它就是一个 upper bound。那刚好你现在有一个 matching， 它的大小就刚好跟某一个 verse cover 是一样大的，那就代表你现在那个 matching 就已经是最大的，不可能会有人比它更大 ，OK？ 所以你也可以想，比如说反证法，如果这个不是最大的，假设还有一个更大的，那就代表说你有一个 matching 它的大小超过某一个 verse cover 的大小，这是不可能 ，OK？ 所以如果你想要的话，你也可以用这样子去说明。Okay, so now our mission is to find this verse cover. Okay. So I'll just give you the construction for this verse cover. So the verse cover will be x minus s union t. So we can draw a graph like this. Okay, so we have two sets in the bipolar graph, x and y. And we have a subset s and t. So recall that S are the vertices that you can visit it or reach it, or can be reached using alternating path, starting from unsaturated vertices in X. Okay, and T just similarly, these are the vertices in Y that can be reached using alternating path. Okay, so you also have vertices that are not in S and T, okay? So we have x minus S, or y minus T. Okay. So to construct a vertex cover, we're going to take these two sets, okay? And then we'll prove that these two sets combined is a vertex cover, okay? And recall that this is a bipolar graph, okay? So all the edges are between x and y. Okay, so perhaps before we consider the proof, we can consider an example. Okay. Okay, so let's consider this example. Okay, and let's try to find S and T. Okay. So to find S and T, first of all, you have to find the unsaturated vertices in X. So this vertex is in U. Therefore, it is in S. Okay. So in the first round, we can only pick this vertex and then go down. So this vertex is in T, and then we can go up. So this is in S. Okay. And then in the second round, we're going to consider this vertex and want to go down. But in this case, we cannot go down because all the edges incident to this vertex are in the matching. So we don't need to do the second round, okay? And the algorithm just stops because there's no other vertices in S, okay? So we have 2 vertices in S and 1 in T. Okay. So according to our construction, in the vertex cover, we're going to pick this vertex, right, because we're going to pick all the vertices in T and all the vertices in X minus S. So this vertex, okay? And we already know that this is a vertex cover, okay? But then we want to prove that in general, this is always true, okay? Okay, so to prove that a set is a vertex cover, you have to consider like all possible edges and show that every possible edge is covered by C, okay? So we can actually, since we have 4 sets here, we can divide this set of edges into 4 subsets. Okay. So we can divide the edge set into 4 subsets. Okay. So the first subset are the edges between S and T. Okay. And then we have edges between S and Y minus T. And then we have edges between X minus S and T. And the final set is between XS and Y minus T. Okay. So we have 4 possible subsets. And once again, this is a bipolar graph, so we cannot have edges between S and X minus S. Similarly, we cannot have edges between T and Y minus T because we consider bipolar graphs. Okay. So then we only need to check whether we can cover all these possible edges. Okay. So the first set is S between S and T. So can we cover an edge between S and T by this set, C? Yes, because we've chosen all the vertices in T, so we can cover S and T. Okay. And the second set is S and Y minus T. Right, so for the second set, it's not so clear, okay? So we'll first consider the third one, okay? So the third set is between X minus S and T, okay? This is between these 2 yellow sets. So apparently, because we actually choose both endpoints of this type of edges, so yes, we can cover these edges, okay? And the last set is between X minus S and Y minus T. So once again, because we've chosen all the endpoints, or all the vertices in X minus S, so we can also cover the edges between X minus S and Y minus T. So now the only question is, so how about these edges, the edges between S and Y minus T? That is edges like this, Okay, so if there indeed exists this kind of edges between S and Y minus T, then our vertex cover, well, it is no longer a vertex cover because we cannot cover this edge. So actually, we're going to prove that we cannot have edges like this. OK， 所以我们目前做的事情是这样，就是我们要去做一个 vertex cover。OK， 所以你要做 vertex cover， 你就要确保每一个 edge 都会被 cover。那我们现在把 edge 做一些分类，根据它所属的 set。OK， 就 S 到 T、S 到 Y 减 T、X 减 S 到 T， 那都没有问题。剩下唯一的可能就是介于 S 跟 Y 减 T 的。这个 S 跟 Y 减 T 的正好就是我们没有办法 cover 到。所以我们接下来就要去说明说，事实上不可能会有 edge 在里面。我们可以回到前面那个例子 ，OK。所以这个是 S， 然后这个是 Y 减 T。所以你会看到，至少在这个例子里面 ，S 并没有边连到 Y 减 T。OK， 所有 S 的边都连到 T。OK，S 没有边连到 Y 减 T。所以至少在这个例子是成立的。当然，我们需要一个比较 general 的说明说，不管你的 input 长怎么样 ，S 跟 Y 减 T 中间一定不会有边相邻。所以有人可以看得出为什么这 proof 其实只要一句话而已，只有一句话。这句话是什么意思？没有一条被选起来的。
我们考虑假设 S 到 Y 减 T 中间有边。
假设它有边 ，OK。
然后，那如果这一条边是没有匹配的话，
所以你要那等一下你会考虑的状况是有被 match 吗 ？OK， 所以你分两个 case。
对，那如果没有被匹配的话，
好。
在我们前面执行的时候，它应该会被加到 T 的那个集合里面，所以矛盾。
谁应该要被加到 T 里面？
就是那一条边连到的那个 Y 减 T 的点。
好。
应该会加到 T 里面，因为我们的演算法是走到 S 之后，然后会走位没有匹配的点。
OK， 好。
它应该会被加到 T 里面去。
这样
矛盾。然后如果它有被匹配的话，但是因为我们 S 集合里面的点都是从 T 轴有匹配的边上来的。
对。
所以呢，这样的话，那个点它同时匹配了两条边。
OK，没错，大致的 argument 就是这样。简单说，最后的结论就是这个 Y 减 T 就这个点，它应该要被放到 T 里面。那为什么有一个比较更简单的说明，就是我们刚刚前面提到的那个 property， 就是说 T 是什么 ？T 就是那些 S 所有的邻居。OK， 只要你是 S 的邻居，你就一定会被放到 T 里面。所以这个 vertex， 如果这边真的有一个点在这边的话，这个 vertex 它事实上不会在 Y 减 T， 它会在 T 里面。OK， 所以这不可能。OK。Okay, so the proof is quite easy. So let's suppose that let's prove by contradiction. Okay, so let's assume that there's an edge between S and Y minus T, and let's call these two endpoints A and B. Okay, so according to our previous property, we know that B is actually a neighbor of A, which is a vertex in S. So according to our previous property, B should be in T. So that's a contradiction. Okay. All right, so now we know that this set C is really a vertex cover. But then we're not done yet. Okay, we have to show that the size of this vertex cover, C, is equal to the size of the matching M. Okay. So in this example, we can see that the size of the matching is 2 and the size of the vertex cover is 2. So they are the same. Okay. Okay. But then we need to have a general proof to show that this holds for any graph. Okay, so how to show that the size of vertex cover is equal to the size of the matching? So whenever you see an equality, you can always think of this as two inequalities. Okay, so we already know that the size of any vertex cover is an upper bound for the size of any matching. So we already know the size of C cannot be less than the size of the matching. Okay. So therefore, we only need to show that So we only need to show that the size of the vertex cover is at most the size of the matching. So then we have this equality. Okay. Okay, so how to show that the size of the vertex cover is at most the size of the matching? So first of all, I claim that all these vertices in C, they are saturated. And recall that what is C? C is T union X minus S. So can you see why? So let's go back to the example, okay? So this is T, this is X minus S. So you can see that these two vertices are saturated, okay? They are like matched by these two edges in the matching, okay? But in general, why? Why it must be the case that T and X minus S are saturated.所以我们现在有两个 set， 第一个是 T， 然后另外一个是 X 减 S。所以这边我再次回忆一下，就是这边我们的假设是这个演算法找不到 augmenting path，OK， 只有在这个时候我们才会去考虑说这个演算法是对的。所以这里的前提是演算法找不到 augmenting path。所以根据这个假设，为什么 T 跟 X 减 S 它们一定都会被 saturated？ 有没有可能其中某一个点没有被 saturated？ 所以我们先来看 T，OK？ T 有没有可能有一个点没有被 saturated？ 有没有？它就是换句话说没有被那个 matching 就是 match 到。OK， 为什么？ OK， 如果有一个 vertex 在 T 里面，然后它没有被 saturate， 那根据我们之前的演算法，那就代表我们已经找到一个 augmenting path。OK， 所以，但是我们刚刚已经强调，就是我们的演算法找不到 augmenting path。OK， 所以所有的在 T 里面的点一定都会是 saturate。Okay. So now we know that all the vertices in T they must be saturated by M. How about X minus S? Is it possible that some vertex in X minus S is not saturated? So 我们接下来就要考虑 X 减 S， 所以 X 减 S 在这边的话就是上面这个 ，OK， 也就是那些不在 S 里面的点。如果你不在 S 里面，你有没有可能没有被 saturate？ OK， 所以为什么？违反哪个定义？
因为它就是因为它不是 saturate， 它才会被选到 SKX。
就是因为它不是这样。
saturated， 所以它才会被选到 SKX。
就是因为它不是，可是它被 saturate， 它有在这个例子它有被 saturate， 它有被 match。
就是因为它 saturate， 它才会被选到 SKX。
也不一定，因为 S 里面有可能有 saturate， 也有可能没有 saturate。对。如果我们今天有一个点，它没有被 saturate， 那它一定会放在哪里？为什么？对，因为我们第一步就把所有没有被 saturate 放到 U， 然后 U 就一定会被放到 S，OK？ 所以换句话说，这个 X 减 S 的，它一定全部都会被 saturate， 因为如果里面有一个点它没有被 saturate， 那其实它应该被放到 U， 那它就应该要被放到 S，OK？Okay. Let's finish the proof here and then we take a break, okay? So now we know that all these verses in T and X minus S, they are saturated, okay? Now, we only need to claim that they cannot be like matched by the same edge in the matching. In other words, for all these vertices, they are instant to different edges in the matching. In other words, you cannot have edges like this. So this is T and this is X minus S. We know that they are saturated. Okay. So for every vertex, we can find an edge instant to it, and these edges are in the matching. Okay. So all we have to do is just show that they cannot share some edge in the matching. Okay. So they can only be matched or instant to different edges in the matching. So if they are matched or instant to different edges in the matching, then we know that the size of the matching is greater than or equal to the size of the vertex cover. Okay. Okay. Right. And also we know that the reason we can have the next chem is that first we have shown that they are all saturated. Okay. So if all these vertices are saturated, then they must be matched by the matching. So therefore we can consider this claim, which says they are actually matched or instant to different edges in the matching. Okay. So in other words, we want to show that we cannot have some vertex in X minus S and some vertex in T such that they are matched by one edge in the matching.对，所以我们刚刚前面的 claim 说的事情就是这个 vertex cover 它一定都会被 saturate， 所以它们都一定会有边是在matching 里面。那我们最终目标就是要去看说这个 m 的大小会大于等于 m，OK， 所以我们要确保说 matching 的边会比较多个 ，OK。那我要怎么确保这件事情？就是我要帮每一个 vertex cover 的 vertex 都找到一个独立的、单独的一个 matching 的边。所以如果可以做到这件事情，每一个 vertex cover 的点，我都可以帮他找到一个 edge， 然后这个 edge 不会共用 ，OK？ 那我就可以说明说 matching 的边会比 vertex cover 的大小还来得大 ，OK？ 那要做到这件事情，就第一个我们刚才已经说，就是它们都会被 saturate， 所以一定每一个点上面 T 跟 X 减 S， 它一定都可以找到一个边是在 matching 的。那关键只是它们会不会共用 ，OK？ 所以我们接下来要说明就是，这个共用的这种边它一定不会存在。所以这个也蛮简单，因为如果这个边是在 matching 里面，然后这个是在 T， 所以根据我们刚刚的演算法，当我们把这个点加进去。然后因为这个边，因为我们先往下走走到这个点，我们接着再往上的时候，我们就会用 matching 里面的边，所以我们就会往上。那往上之后就会导致说这个点，它事实上就会被加到 S 里面 ，OK， 所以就不可能 ，OK。所以答案就是这个 U 应该要在 S 里面 ，OK。所以每一个边每一个 verse cover 的点，它一定会连到不同的 matching 的边 ，OK。所以这样我们就可以建立刚刚的那个关系，就是我就写这样。OK， 所以这样我们第3个问题就回答完 ，OK。所以每一次我们的演算法找不到 augmenting path 的时候，你去看 y 里面你去看那个 t 还有 x 减 s， 你就会发现它是一个 verse cover， 然后它的大小跟你的 matching 是一样大，所以就代表你的 matching 就已经是最大。好，所以我们就有点 delay， 所以我们就20分的时候再开始。
前面在讲这个 C 这个部分。
对。
我想问为什么这个可以讲这个
？OK， 所以你现在手上有一个 matching， 随便一个 matching， 然后随便一个 verse cover。所以假设这个 matching 它有3个边，那 verse cover 它的目标是要去 cover 所有的边嘛？这个 graph 的所有边。那当然你为了要 cover 所有边，你就必须要 cover matching 里面那个边。那因为这个 matching 的边它都不会共用端点，所以你如果想要光是要 cover 这个 matching 里面的边这3个，你就铁定会需要3个 vertex 才可以 cover。
哦，是这个意思。
对。
比我讲直觉很多哈。那再往前，我可以看一下。
往前还是往
下？
往下。
看一下后面，就刚刚讲的。
OK。这页是要讲所有 verse cover。
就已经讲到，就是刚刚那个。
对。
所以现在只要 prove 这个就可以等号。
对。我们要 prove 它的 idea 就是帮每一个 C 里面的点都找，因为这个有点像是你如果要证明一个 set 比较小，另外一个 set 比较大，你就可以帮每一个这个比较小的 set 找到一个类似 1 to 1的 mapping 到另外一个 set， 那这样子你就可以证明这个比较小，这个另外一个比较大。所以我们这边要找就是。
那就等于了，如果是 1 to 1的
话。应该我有点忘记那个术语是什么，但是就是他们一定不会 map 到同样的点。对。所以我们要做就是每一个 verse cover 的点，我要帮他找一个 edge。对。
所以这一句来讲，他们都是被染色而已。那这个图是什么意思？
这个图要说的就是下一个我要说的就是，因为我们现在可以确定说这个 T 跟 X 减 S 里面每一个点，它们都有被 saturate，
对，
所以它们都有，所以这个
就是都有碰到 matching 的边。
对，都有，所以我画出来红色这些就是 matching 的边。对，这个就是 matching 的边。M。对。那我们现在要确保就是不会说有，像这边的话 T 就有3个点嘛 ，X 减 S 有3个点嘛，所以但是你看如果是这样的话 ，matching 只有5个边而已，就没有达到我们想要的效果。我们想要的效果是每一个 matching 的每一个 verse cover 它
就要确保 T 和 S 之间 X 就这2个 set 之间没有任何的 matching。
可以是这样说，对。换句话说。也对你这个说法搞不好更好，就是我们要说明就是 matching 不会去 match T 给 T 减 给 X 减 S，对，他们不会，对 matching 不会介于这两个边的，对。matching 不会介于这两个 set，sorry。
可是这样跟 C 小于等于 N 有什么关系啊？
所以这边就是要就是我先画这个，所以这是 C。OK， 那我们要怎么说 C 比较小 ，M 比较大？我们要做的事情事实上是，我帮每一个 C 的点都找一个 matching 的边，而且这些不会共用。那这样子 match 的边就只有可能会比 verse cover 更大，不可能更小。OK， 再说一次，就是我们要说明的是这个红色这5个红色点的这个 set 比黄色的 edge matching 的 edge 要来的更小，这我们要说明是。那为了要说明这件事情，我们要说的就是帮每一个这个红色的点找到一个伴侣，就是找到一个跟他 associate 给他的一个 edge。然后这些 edge 都不会说一个 edge 给2个人用，所以如果你可以找到这种配对，那是就代表你事实上有很多个 matching 的边，你才可以做这件事情。对，所以这样就代表 matching 的边会比这个红色的点更多。我用另外一个比喻好了，假设你有一个 set 是人，另外一个 set 是狗好了。然后我们现在想要说明的是，人比狗还得多，狗比较少，人比较多。那你要怎么证明这件事情？你就可以帮每一只狗类似配对一个主人，那我们要确保说这个主人每个人最多只能领一条狗，就换句话说，他们不会共用主人。所以如果你可以真的分配给每一条狗一个主人，那是就代表说，事实上你的主人的个数一定会比人的更多。
狗更多，
对，比狗更多，对，所以同样的 idea， 所以这边也是，所以这就是我刚刚说要去建立这个 mapping， 对，那所以我们的目标就是要去说明说，我可以帮每一个点找到一个 matching 的边，然后这每一个人找到的，我帮他找到那个 matching 的边都是不一样的，这样子我就结束了。对，所以现在就看为什么，所以为什么就是刚刚这个。所以首先，因为我们前面已经说它都有被 saturate， 所以它铁定可以找到一个边，只是说这个边会不会跟其他人共用，这我觉得还不是很确定。至少在这一页我还不确定，但是我在这一页可以确定，真的它一定可以找到一个边。那下一页这边要说的就是这个边不会共用。那很明显，这我没有特别讲，就是 T 啊 ，T 自己找的一定不会共用，因为这是 biparallel graph，T 之间的这些它一定根本不会 H， 所以唯一有可能共用的状况就是发生在 T 跟 X 减 S。对。
哦，那这样确实就是大于小于等于。
对。
等一下，我再想一下哦。
对，你可以再消化吸收一下。
T 为什么一定是 saturate？ 再回去。
OK， 好。
就看一下 T 为什么一定是 saturate。
OK，T 一定会 saturate 的原因是因为如果 T 有一个点没有被 saturate，那这个演算法当它 reach 那个点的时候，它发现它没有被 saturate，我们事实上就会找到 augmenting path。但是我们刚刚的假设是没有 augmenting path， 对，所以 T 一定会被 saturate。
好，那就可以。好，
对，
我懂了。
对 ，OK。 All right, so let's get started. Okay, so I think there's a principle behind this proof, okay? So whenever you want to prove a set, say A is smaller than the other set B, you can do the following, okay? So you have two sets, A and B, okay? You want to prove that A is smaller than B. So you can always imagine that A is just like a set of boxes, and B is a set of balls. Okay, so you have balls. I think perhaps I should change it to bins. Okay, so yeah, usually we'll use balls and bins. Okay, so we can put balls into bins. Okay, and in this case we want to prove that B is larger than A. So how to do this? So all you have to do is to show that for every bin you can put one ball in it. And clearly, you cannot put a ball into multiple bins because you cannot like split a ball or break a ball. Okay, so a ball is in exactly one bin. Okay. So once you have established this relationship that you can have a ball in every bin, this already shows that you have more balls than bins. Okay. So in our previous proof, the set A is C, and the set B is the matching M, okay? So for every vertex, that is for every bin in C, you want to find a ball, and in our previous context, the ball refers to the edge in the matching, okay? So I want to show that for every bin, we can find a unique edge to put the ball into the bin. Okay. Okay, so we have answered the last question. That is, whenever our algorithm cannot find an M augmenting path, this shows that the matching we have is the maximum matching. Okay. Because we can find a vertex cover whose size equals the size of the matching. Okay. So this also shows this result. Okay. So because we only consider bipartite graph, and our algorithm can produce M star, which is the maximum matching, and we can find a minimum vertex cover, C star. Okay. So C star is just the union of T and X minus S, okay? And we just proved that these two sets have the same size, okay? So, yeah, this result is true for all bipartite graphs. Okay, so now we've considered algorithms that can find the maximum matching. But in some bipartite graphs, we can actually find like a perfect matching. So a perfect matching is a matching where you can saturate all the vertices. That is, all the vertices can be matched. Okay. So for example, if you have this So you have this bipolar graph, then I think it's easy to see that we can have a perfect matching like this. Okay, so in this matching, it saturates all the vertices. Okay. So clearly not all graphs have perfect matchings. For example, like the previous one. Okay. So in this bipolar graph, we cannot have a perfect matching because the maximum matching only has 2 edges. So we can at most saturate 4 of them. Okay. So okay. So given a graph, you can obviously use the previous maximum matching problem to find or to test whether there's a perfect matching. Okay. So we are not talking about the algorithm design problem. So next we're going to identify some necessary and sufficient condition for the existence of perfect matching. Okay. So let's once again consider this graph, which has no perfect matching. Okay. So one way to show that this graph has no perfect matching is clearly to find the maximum matching, and then it's clear that it has no perfect matching. Okay. But here I want to have a simple proof to show that this one has no perfect matching. So 大家可以看出来说这个 graph 为什么没有 perfect matching 了。所以当然你可以去把 maximum matching 找出来，然后再说 maximum matching 不是这里的 maximum matching 没办法 saturate 所有点，这当然是一个方法，可是这个比较慢一点 ，OK？ 所以我想要一个很简单、直截了当的说明，大家一听就知道，哎，对，你说的没错，这个不可能有 perfect matching。所以有人有什么想法吗？这应该不会太难。你要怎么说明？你一定不可能找到一个 matching 它 saturate 所有的点。有想法吗？哎，这样也是差不多一样的意思，因为 vertex cover 的大小就会跟 maximum cover 是有一点关系的嘛。对。 我要一个超级简单的说明。是太简单，所以大家觉得不可能是答案，还是？就只要一句话而已，这句话就可以证明这个 graph 不会有 perfect matching。哈？对，只是这个。B、C 跟 D、E 他们连到同 degree 是1，那啊哈 ，OK。对，那为什么为什么这样就一定不会有 perfect matching？
其中一个 B、C、D 其中就 B、C 跟 D 各其中一个都不可能会，他们两个不可能同时被 match。
所以如果 B 跟 C 如果有 perfect matching， 那 B 跟 C 一定都要被 match 到。那可是如果 B 跟 C 都要被 match 到，那 B 跟 C 铁定他们就要有2个不同的邻居，但他们这边只有1个邻居。OK， 那如果今天我把问题稍微改成这样子。我现在开始稍微有点复杂了 ，OK。所以你们一样也是一句话就跟我解释为什么不可能会有 perfect matching。所以在这个例子里面没有一个点 degree 是1的 ，OK。所以大家至少都有2个邻居。有什么想法吗？B、C 跟 G 啊哈，啊哈，所以这样为什么就代表没有 perfect matching？ OK。所以这边有一个关键，就是刚刚我们有特别去看 degree 1，这个 degree 1的资讯其实不是特别的重要，所以这边的关键是他们有几个邻居。OK， 所以每次你可以找到一个 set， 然后它邻居比较少，比那个 set 更小，你就知道它一定不会有perfect matching。OK。Okay, so I think the special property here is that we can find a special set. Like in this case, B, C, G, okay? So the special property about this set is that the number of its neighbors is less than the size of the set, okay? So in this case, the size of set is 3, while the number of neighbors is only 2, okay? But in order to saturate 3 different vertices, you have to have at least 3 neighbors, okay? So this shows that we cannot have a perfect matching in this graph, okay? So in general, I will call this kind of set the bad set, okay? So a bad set is a set such that so here n of s is the set of s, the set of neighbors of s, okay? So this is just the number of neighbors of s, and this is the size of s, okay? So whenever you have this kind of bad sets, this immediately tells you that you're not going to find a perfect matching, okay? Okay. So now we have one direction here. Next, we can consider the other direction where we try to prove this direction. So suppose there's no bad set, okay? Then can you show that there must be a perfect matching? Okay. And this condition that there's no bad set, this is called Hall's condition. Okay. And this result is called Hall's theorem. Okay. So actually we can slightly generalize this result because here we once again, we only consider bipolar graphs, okay? And in order for bipolar graphs to have perfect matching, the two sets x and y, they must have the same size, okay? Because if x is smaller than y, then you cannot saturate all the vertices in y, okay? So we're going to consider the next slightly generalized result. Okay, so we're going to consider the case where x can be smaller than y, okay? So once again, a bipolar graph, and but this bipolar graph may not be balanced. By balanced, I mean they have x and y have the same size, okay? So in this claim, they can have different sizes. So next, I'm going to give a formal definition for this statement that there's no bad set, okay? So if for every subset, let's call it A, or let's call it B, okay, so we want to check all the possible subsets of X to see whether it is a bad set. Okay. So this says that the set B is actually larger than its number of neighbors. Okay. And now since X and Y, they can have different sizes, we cannot wish for a perfect matching, okay? The best we can do is to find a matching that saturates the smaller set, in this case, X, okay? Okay? And this highlighted part is like the formal definition for there's no bad set. So if there's no bad set, then for any subset you choose, it must have like enough neighbors, okay? No. Sorry. So we must have enough neighbors to create the matching. Okay, sorry. Okay. Okay, so next we're going to prove this claim, okay? So the setup is that we have a bipolar graph. X is smaller than Y, so visually this looks like this, okay? So we have X and we have Y, okay? And we can check all the subsets in X, and we are told that they have enough neighbors, okay, such that the number of neighbors is greater than the size of the sets, okay? And this holds for every possible subset of X. So the informal statement will be like, if for every subset, the set has enough neighbors, it has many neighbors, then we can always find a matching that saturates X, okay? So this is what we're going to prove next. 好，所以接下来我觉得这个 statement 虽然说看起来蛮长的，但其实它背后要传递的资讯很简单，就是你有一个 bipolar graph， 然后我们现在的目标是要去找不是 perfect matching， 是只要 saturate 所有 x 里面的点就可以了。然后我们有的资讯是 x， 你随便挑一个 subset， 这个 subset 它都有很多个邻居 ，OK？ 当然因为这是 bipartite graph，所以它的邻居一定都在 Y 里面。OK， 然后不管你怎么选这个 subset， 它的邻居都很多。直觉上来讲，这就代表说它应该蛮容易找到一个 matching 可以去 saturate 这个整个 set X。OK， 我们等一下要做的事情就是去说明这个直觉确实是对的。OK。OK。Okay, so to prove this claim, we're going to consider the contrapositive of the claim. Contrapositive is like, sorry, 若 P 则 Q， 非 Q 则非 P 这样子 ，OK。So the contrapositive of this statement Okay. So the contrapositive, to find a contrapositive, we have to find like the negation of the statements here. So this is Q, and this is P. Okay. So the negation of Q is simply that there's no matching that can saturate X. Okay. The negation of P will be, well, informally this says that there's no bad set. So the negation will be there's a bad set. Okay. Okay, since this is a bad set, this means that it has only a few neighbors. Okay. Okay. So the neighbors of B, it's not enough. Okay, so by not enough, this means that the number of neighbors is less than the size of B. Okay. So this is the contrapositive of the previous statement. Okay. So now the assumption is that we have a graph, a bipolar graph, such that there's no way to saturate X. Okay. Some vertices in X must be unsaturated. Okay. So in this case, we want to prove that there must be a bad set. Okay. So in this proof, all we have to do is just to construct this bad set. Okay. Okay. So let's first consider the maximum matching M. Okay. And I stress that according to our assumption, M cannot saturate all the vertices in X. Even if it is the maximum matching. Okay. And then we want to construct the set B. Okay. So I claim. So what should be this vertex, this bed set B? We claim that S is a bed set. What is S? Well, S is the set S that we introduced in the maximum matching algorithm. That is, we start from the set U, and then we will use alternating path to reach vertices in S, in X and Y. So for those vertices in X, they are in S. OK， 所以这边这个 S 就是我们之前那个演算法讲的那个 S。OK。所以就是你从没有被 saturate 的点出发 ，OK， 一定会有没有被 saturate 的点，因为我们刚刚前面讲，我们假设是 x 没有被 saturate， 所以一定可以找到一个没有被 saturate， 从那个点出发走 alternating path，OK， 那这个 alternating path 经过的那些点，如果是在 x 里面，在上面的，它就是在 S 里面，所以我们现在要说的是，这 S 它就会是一个 bed set。所以如果一直用我们前面的 example， okay. So in this example, we have these two vertices in S, and it's clear that these two vertices, they form a bed set because the size of S here is 2, and they only have one neighbor. Okay. So similarly, if you consider, well, not this one, okay. Yeah, let's just consider this one. Okay, so next we're going to prove that S is a bed set. Okay, if the set X cannot be saturated. So in this case, you can see that this guy here cannot be saturated. So we have a bed set, okay? And recall that we know that T is a neighbor. T is just the set of neighbors of S. Okay. So to prove a set is a bed set, all we have to do is to show that it has only a few neighbors. Okay. So the number of neighbors is less than the size of S, and then the proof is finished. Okay. So all we have to do is to show that the size of T is less than the size of S, and we're done. Okay. 所以 bed set 就代表你有很多个 vertex， 但是它们只有一点点邻居，所以你就没办法 saturate 这个 set。所以我们现在要说的是，我们这里演算法那个 S 它其实就是一个 bed set。如果这个 graph 没办法 saturate X 的话 ，OK， 所以它就会是 bed set。那要怎么说明它是 bed set？ 你就把它邻居全部找出来嘛，看一下它邻居是真的很少。那像这个例子里面，它邻居就真的很少，就只有一个点 ，OK。那当然，接下来我们就是要一个比较 general 的 argument 去说明说，不管你的这个 graph 长怎么样，它的邻居就是这个 t， 一定不会很多，一定会小于 S 的大小。So actually, this proof is quite easy. Okay, so if you recall, the reason that we can have these vertices in T is because we can reach it from alternating path, okay? And this is a maximum matching. So all the vertices in T are saturated. Okay? Because M is maximum matching. So if there's some vertex in T that is not saturated, then actually we can find a larger matching. So yeah, all the vertices in T must be saturated, okay? So recall that in our algorithm, whenever we find a vertex in T that is saturated, we can then go up, okay? And then add the other endpoint to the set S, okay? So in other words, all the vertices in T, they are actually matched to vertices in S. Okay? So this already tells you that the size of T cannot be greater than the size of S. Okay? Because for every vertex in T, you can use the matching edge to reach a vertex in S. Okay? But we are not finished yet because we want to prove that the size of T is strictly less than the size of S. Okay? So we need one more observation. Because according to this argument, it may be the case that T and S, they have the same size. Okay? Next, we want to argue that no, this is impossible. T and S, they cannot have the same size. And there's a very simple reason for that. Right, U, right. So the reason is that S also contains U as a subset. And yeah, that's right. Okay, so but S also contains U. Okay, so the reason that we have U is because M cannot saturate X, so U cannot be empty. Okay. So the size of T must be strictly less than the size of S. Okay. And that's it, okay? So that's the proof. So see, we use this set S and T to prove multiple things. So first of all, we use it to show that the algorithm is actually optimal in the sense that whenever the algorithm cannot find augmenting path, it uses S and T to build this vertex cover, which is the same size as the matching we have, okay? And then we use S and T to prove Hall's theorem, okay? So in this case, S is the bad set, okay? All right, okay, so let's take a break, and when we come back, we're going to consider a simple application of Hall's theorem. Right. So let's take a break. Right. Okay. So let's continue. Okay. So in this host theorem, the informal idea is that if every set has enough neighbors, then we should be able to find a perfect matching. Okay. So next I'm going to discuss a very simple application. Of host theorem. Okay. Okay. So in this application, we're going to consider what we call the R regular bipolar graph. So R regular means every vertex has exactly R neighbors. In other words, all the degrees are R, okay? So for example, this is okay. So this is a two regular graph because every vertex has exactly two neighbors. So this is two regular. Okay. So we're going to show that for every R regular bipolar graph, we can actually find a perfect matching. So clearly, to have a matching for every vertex, you should have at least one neighbor. So the degree should be at least 1. So we only consider the case where R is at least 1. Okay? Because when R is 0, which is 0 regular graph, then there's just no edge in the graph. Okay? Okay, so for example, like this graph, we can have this matching. Okay, so this matching is a perfect matching because it saturates all the vertices. Okay. And so actually there are many different ways to draw our regular graphs. Okay, so yeah, so this is a nice result, and we're going to use host theorem to prove that we can always have a perfect matching. Okay. And recall that for a bipolar graph to have a perfect matching, we have to have, like, let's say, the set of X, the set X and the set Y, they have the same size. Okay. Otherwise, if one of them is smaller, then we cannot have a perfect matching. So first, we have to, before we can show that, we have to show that X and Y, they have the same size. In other words, the size of X equals the size of Y. Okay. Clearly, under this R regular condition, where R is at least 1. Okay. Okay, so from this example, you can see clearly that X and Y they all have three vertices. Okay, so they have the same size. So we want to show that in general this is true for all R regular graphs when R is at least 1. Okay. 所以这边我们要做的事情就是要考虑这种 R regular 的 bipolar graph。 那如果要说明它是 perfect matching，在那之前我们可能要先考虑一个更简单的问题，就是有没有可能你可以画出一个 R regular， 譬如说 two regular 的 bipartite graph， 但在这个 bipartite graph 里面 x 比较小 ，y 比较大。如果你可以画出这样的 graph，x 比较小 ，y 比较大，然后它们的 degree 都是2，那这样就绝对不可能有 perfect matching，OK？、所以为什么不可能？哦 ，OK， 所以你可以看出来为什么不可能吗？有没有可能画一个 bipartite graph，x 比较少 ，y 比较大，这样就没办法。对，所以没错，就是如果要有 perfect matching，x 跟 y 铁定要一样大。对，所以我们现在要先想办法说明说 x 跟 y 至少一定会是一样大，不然后面你也不用去思考。我们的策略是这样，就是你要说明它是 perfect matching， 我们会先做第一件事情就是 x 跟 y 一样大，然后再来我们会说会有一个 matching saturate x， 那这样子我们就有 perfect matching。所以，但 anyway 不管就算后面不管策略怎么样，你要 perfect matching， 你铁定第一个要保证就是它们也要一样大，不然后面就没戏唱。OK， 所以我们需要一个简单的 argument 去说明 x 跟 y 它的大小一定会是一样。这样清楚 ？OK 啊 ，OK。x 先选一个点。
先假设先放一个点进去。
OK。
然后因为它是 R regular， 所以它至少会有 R regular。
对。
然后把它全部都放进 Y。
对。
那这样的话，就知道 Y 的那个 size 会是 R。
对。
那我表示说我的 x 如果要大于 Y 的话，
啊哈。
x 要大于 Y 的话，所以 x 至少要 R 加一个点。
啊哈。
然后 R 加一个点，它的边数会是 R 加一乘以 R， 然后下面的边数只有，上面的 degree 会是 R 加一乘以 R， 下面的 degree 会是 R 乘 R， 所以呢，它就会爆掉。
但你还是永远可以继续加。对，所以你有提到一个关键就是 degree， 所以所以这边我们一样会需要有一个切入点，要有一个 handle， 那个 handle 就是要去看 degree。所以可以看出来怎么利用 degree， 当然什么的 degree 我们要讲了，但关键是要看 degree。OK， 为什么？
因为 x 跟 y 它是大的 bipartite graph， 所以它的中间不会相连，所以它都会 degree。
没错，所以这边的关键就是 x 跟 y 它的 total degree 会是一样 ，OK， 因为它是 bipartite graph。Okay. So what is the total degree of x? Well, because this is a R regular graph, meaning every vertex in x has a degree of R, okay? So the total degree of R is just R times the size of x, okay? And similarly, the total degree of y will be R times the size of y, okay? Now, since these two quantities are the same, we can cancel out this R, which gives us the result. Okay? Good. So now we know that in a R regular bipartite graph, the size of x must be equal to the size of y. Okay. And I want to stress that R cannot be 0, okay? Because if R is 0, then you cannot cancel out this R, okay? And indeed, if R is 0, you can have like one vertex in X and lots of vertices in Y. Still, it is a 0 regular bipolar graph. So yeah, in this proof, only consider the case where R is at least 1. Okay. So you can divide both sides by R because R is not 0. Okay. Okay. And next, we claim that there is a matching that saturates X. Okay. So combining with the previous claim that the size of X equals the size of Y, we get that there's a perfect matching. Okay. And for this claim, we're going to use Hall's theorem. Okay. Okay, so whenever you want to apply Hall's theorem, all you have to do really is just to show that every set cannot be a bad set. There's no bad set, okay? That's all you have to do. So in other words, for every subset B in X, the size, it has lots of neighbors, okay? So the number of neighbors is at least the size of B. Okay. So it's like every subset is a good set, okay? So this is the real claim that we try to prove, okay? Okay, so let's just fix any subset B of X, okay? So we want to show that the number of B's neighbors is at least the size of B. So how to prove this?所以我们现在要做的事情是随便给你一个 x 的，因为我们要 Hall's theorem， 每次你要 Hall's theorem 就代表你要说每一个 set 都不是 bad set，OK，、每一个 set 都有很多个 neighbors， 所以你一定会有 perfect matching，OK，、所以我们现在要看的就是随便给我一个这个 graph 里面 x 的 subset， 我们叫它 b，OK，、好，我们要做的事情就是要去说，哎 ，b 它 neighbor 其实很多，至少是跟那个 b 的大小是一样，所以这是我们现在要做的事情。所以一样，这个 proof 也很简单，就一句话而已。OK， 所以你可以看得出来要怎么说明这句话。所以一样，我们会需要一个切入点，一个handle。 所以这 handle 一样是 degree。所以这里的关键就是去看 B 的 total degree， 跟 B 的 neighbor 的 total degree。OK， 所以谁比较大？所以一个是 B 的 degree， 有点像 B 的邻居。OK。的个数，然后这有点像是 B 的邻居的邻居的个数，有点这种感觉 ，OK。所以谁的，所以哪一个数字会比较大？左边还是右边？B 的邻居一定包含你自己，你可以把它想成你的朋友的朋友一定有我 ，OK。但是你的朋友的朋友有可能有其他人 ，OK。所以这个你的朋友的朋友一定会更多，一定会比你的朋友更多。所以这句话基本上没有用到什么 R regular 的特性，没有。这个是 apply 在就是所有的 graph 上面，只要你有一群点，你去看这群点的朋友 ，OK， 就是这个，那再去看这些点的朋友，那一定会比较多。OK， 那剩下就跟刚刚一样了 ，OK。OK， 所以你就再把 R 消掉，就可以得到我们想。好，所以这个结果就是 R regular 一定会有 perfect matching 的结果。如果没有 Hall's theorem， 我是也不知道怎么证了，但是看起来就没有那么简单 ，OK。但是一旦你有 Hall's theorem， 这个就会变得很简单 ，OK。有问题吗？所以到今天目前为止，我们就把我们刚刚那个 maximum matching 的演算法讲完，然后我们去看算是 maximum matching 的一个特例，就是 perfect matching，OK。对 ，perfect matching 就是你可以 saturate 所有点 ，OK。然后我们也去看它的一些充要条件 ，OK。有问题吗 ？OK， 如果没有的话，我们就去看下一个 topic。So our next topic is actually a generalization of the maximum matching problem. Okay, so it is called maximum weighted matching. So in this problem, edges have weights. Okay, so there are numbers associated with every edge, and we want to have the matching that has the highest total weight. Okay. So the input is edge weighted bipolar graph. Okay, and we're going to use W to denote the edge weight. Okay. So for example, so in this graph, we're going to write, for example, WAD is 2, and WBC is 3, okay? So W stands for weight, okay? And the output is a matching M such that the total weight of the edges in the matching is maximized. Okay. So if all the edge weights are just 1, okay, then it degenerates into the maximum matching problem we studied before. Okay. So here we only consider, we mainly focus on the case where edge weights are different. Okay. Okay, so before we discuss the algorithm, I want to make some assumptions about the input to simplify the algorithms a little bit. So we will have 2 assumptions. And these 2 assumptions hold without loss of any generality. Okay. The first assumption is that we only consider balanced bipartite graph. That is, the size of x equals the size of y. Okay. So then you may think, okay, so what happens when x and y, they have different sizes? Like this one. Okay. Well, in this case, we can just add some dummy vertex, all right, like this. Okay, so this is a dummy vertex. Its purpose is just to make x and y having the same size. Okay. Okay. So we can always assume that the size of x equals the size of y. Okay. And the second assumption that we're going to make is that the bipartite graph is complete. Okay, so it's a complete bipartite graph. So a complete bipartite graph means that for every vertex in x and every vertex in y, there's an edge. Okay, there's an edge connecting these 2 vertices. So for example, this graph is not a complete bipartite graph because some edge is missing. Okay. So to satisfy this assumption, we just add some, again, dummy edges. Okay. Okay, so in the example here, we can just add these blue edges. Okay, and these blue edges have weight of 0. Okay, so it does not change the solution. Okay. So the reason that I want to have these 2 assumptions is that according to this, based on these 2 assumptions, I can always assume that the best matching is always a perfect matching. So I'm going to just write MWM. So this stands for maximum weighted matching. So the maximum weighted matching is a perfect matching. Okay. So based on the assumptions, we want to find a perfect matching that has the highest total weight. And yeah, so this is the problem that we're going to consider next. Okay. So before I tell you the algorithm, recall that in the previous algorithm for the maximum matching problem, to show that the matching we have is the best, we have to create some upper bound. In that case, we consider vertex cover. Okay. Similarly, for this problem, we have to consider an upper bound. Okay. So let's consider this upper bound first. Okay. So for the previous problem, we consider vertex cover. That is when the case when edges do not have weight. Okay. But now edges have weight. So we're going to slightly generalize vertex cover so that you also have weights. Okay. So we have weights on vertices. So it's called weighted vertex cover. Okay, so a weighted vertex cover is not a subset of the vertex set, no. In a weighted vertex cover, you actually assign weights to vertices, okay? Okay. So again, in this weighted vertex cover problem, you want to cover edges. But now, since edges have weights, you want to assign sufficiently large weights to the two endpoints of the edge so that the total weights is greater than or equal to the edge weights. Okay? So in this case, we can have a weighted vertex cover like this, okay? So in this weighted vertex cover, I assign a weight of 2 to A, and 0 to C, 0 to D, and 4 to B, okay? So you can see that you can actually check all the possible edges, and you'll find out that the total weight of the two endpoints must be greater than or equal to the edge weights, okay? Okay, so so this is weighted vertex cover. So what is the upper bound for the matching? Okay. Okay, so again, we consider any matching and any weighted vertex cover. Okay, so we have M and C. So C here should be viewed as like an assignment or a function. Okay. All right, so this summation is the total weight of the matching M. Okay, so the upper bound is just the total weight of the vertex cover. Okay, so this is total weight of C. Okay, so this is an upper bound. Okay, so next we're going to prove this inequality, okay? Okay, so here I denote every edge in the form of xi, yj. So xi is a vertex in x, and yj is a vertex in y. Okay. Okay. So this is well just the total weight of the matching. Okay. And the first property we're going to use is this, okay? Because this is a weighted vertex cover, so we can cover every edge, okay? So in this, we use definition of weighted vertex cover. Okay. And I claim that this is at most the total weight of the vertex cover. Okay. So here I consider all the endpoints of a matching, and here I consider in the summation I consider all the vertices in the graph. Okay. So the reason that this holds is because by the definition of matching. Okay, because this is a matching, so we never consider the same endpoint twice in this summation. Okay, so for every endpoint considered in the summation, we consider it only once at most. So this is certainly less than or equal to the summation when we consider all the vertices in the graph. Okay. And that's it, okay? So that's a proof. So in this proof, we use the assumption that the weighted vertex cover can cover every edge, and the property that matching edges in the matching do not share endpoints. Okay. Okay, and also if you consider a case where all the edge weights are just 1, then this gives you a proof for the previous upper bound where we want to maximize the number of edges. So in that case, the size of the vertex cover is a vertex cover, is an upper bound. Okay, and yeah, but for that case, C can only be 0 or 1. Okay, So for the case where C can only be 0 or 1, it degenerates into the previous verse cover problem. Okay. 好，所以这边刚刚有点像是把我们之前讲的 verse cover 跟 matching 的关系再稍微推广一下 ，OK？ 推广到我们今天是不是选或不选，是要 assign weight，OK？ 那一样就是我们会用到这个 verse cover 的特性。那我刚好特别说的是verse cover 在前面的 verse cover 我们比较像是选或不选，我们不会 assign weight。所以选或不选，你可以把它想成就是 assign 0或1， 0就是不选，1就是选 ，OK？ 所以这个 inequality 在前面那个例子，它代表就是这两个 endpoint， 我一定至少有一个会选到，因为选到这我刚刚说这里是1嘛，1就代表有这个 edge， 然后这两个加起来至少会是1，就代表这两个里面至少有一个是1，那就代表至少这两个有一个会被选到 ，OK？ 然后跟之前的 proof 一样的，就是我们会利用到 matching 的 endpoint， 它不会共用的特性。所以如果不会共用的话，你这个 summation 考虑的都不会 double count。OK， 既然不会 double count， 它一定会小于等于当你考虑所有的 vertex 的时候。所以大家可以去比较一下这个 proof 跟前面的 verse cover 是 upper bound 的 proof。OK， 所以这边我们事实上还可以有一个延伸，就是如果我今天说 M 它不是 matching， 它事实上是 perfect matching。那当然也会对。那更重要的事情，如果是 perfect matching 的话，这个不等式就会变成等式。为什么？因为如果它是 perfect matching 的话，那就代表每一个 endpoint 都有在这个 summation 被我考虑到，就这个 graph 的所有的 endpoint 都有被 saturate， 因为这是 perfect matching。既然都有被 saturate， 就代表在这个 summation 我考虑到所有的 vertex， 所以这个就会等于这个。OK。好，那在我们之前講 verse cover 的时候，那个有一个很重要的事情，就是在 bipartite graph 里面，事实上最好的那个 verse cover 会跟最好的 matching 是一样大的 ，OK？ 那这边呢，我们也会希望有一个类似一样的效果，就是最好的 weighted verse cover 它的 total weight 跟最好的 maximum matching 的 weight 是一样大的。那你会看到这边唯一的关键就是这个不等式，因为如果这个不等式变成等式的话，就全部都等于，所以就代表 matching 的 total weight 会跟 verse cover 的 total weight 是一样，所以关键就会出现在这里。OK， 那这个什么时候等号会成立？这个等号成立就代表说这个 edge 它的 weight 刚好会等于那两个 endpoint 的 total weight， 那这个时候它等号就会成立。OK。OK， 所以像这个例子里面，这个 edge weight 是2的这个 edge， 它的特性就是它的 edge weight 是2，两个 endpoint 的total weight 也是2 ，OK， 然后这个4也有满足这个条件，就是这个 edge weight 是4，然后两边的两个 endpoint 的 weight 也是4加0也是4 ，OK， 所以这种 edge 我们叫做 tight edge。对，所以 这下面这就是一个 tight edge， 对 ，edge weight 是3，然后2个 endpoint 的 total weight 加起来也是3 ，OK。所以每次你在看一个 tight edge 的前提，你都是必须要先有一个 weighted vertex cover C，OK， 这样你才可以有2个 vertex cover，2个 endpoint 的 vertex 的 weight，OK。所以我们今天绝对来不及时间讲演算法，然后我们下礼拜会看到，就是想办法让这里的不等式变等式。然后我们刚刚说这里是 perfect matching， 所以我们要的目标是，我们希望有一个 perfect matching， 然后这个 perfect matching 的每一个 edge 都是 tight。我们想要一个 perfect matching M， 还有一个 weighted vertex cover C。OK， 那我希望它每一个edge 都是 tight， 因为这样子就代表 M 就是 maximum weighted matching，OK， 所以我们可以再 go through 刚刚的那次 proof， 所以OK， 所以这个是这个 matching 的 total weight，OK。然后因为这个每一个 edge 都是 tight， 所以这个你去看每一个 edge， 它就会等于2个 endpoint 加起来。OK， 那后面就跟之前是一样，那因为它是 perfect matching， 所以这个就会等于你考虑所有的 vertex， 然后看它的 edge weight 的总和。OK， OK， 好，所以这就告诉你说，你找到一个 matching， 然后它的 total weight 跟某一个 upper bound 是一模一样，那这个 upper bound 就是 weighted vertex cover 的 total weight，OK， 所以就是这个 OK， 所以这就是一个 upper bound， 所以每一次你找到一个 matching， 它跟某个 upper bound 是一模一样，那就代表那个 matching 就是最好。好，所以这就是我们下礼拜的目标。我们下礼拜目标就是要找一个 matching， 不是找一个 matching 而已，我们要找到一个 weighted vertex cover。那这个 weighted vertex cover 会让所有这个 matching 的 edge 都是 tight， 那这样子就已经是一个 proof， 说这个 matching 就会是最好的。OK， 所以如果是在这个例子里面的话，这个首先我们可以 double check 一下 ，OK， 所以应该蛮容易可以看得出来，比如说像这样子，这个就是一个 maximum weighted matching， 它的大小是4，OK， 但是呢，这个 matching 就不是所有的 edge 都是 tight。如果我们现在考虑的是蓝色的这个 weighted vertex cover， 因为它的只有这个 edge 是 tight， 那这个不是，所以你会看到在这个在这个 matching 里面，我们还没有帮他找到一个好的 vertex cover 去证明说它真的就是最好的。 但确实这个是最好的 weighted vertex cover， 但是我们没有那个，这个确实就是最好的那个 weighted matching， 但是我们这边还没有一个证明去跟大家说，这个证就是最好，所以我们会需要去调整这里的 vertex cover 的值，然后去证明说，这个事实上是最好的 ，OK？ 那事实上刚刚这样听起来可能会让大家觉得我那个 weighted vertex cover 只是要去做佐证，去证明说这个 matching 是最好。那事实上在下礼拜我们会看到演算法里面，这个 vertex cover 它会事实上是会引导我们去找到那个我们要的 matching，OK？ 所以它不是只有用来证明而已，它在演算法里面也会扮演重要的角色 ，OK？ 好，所以时间差不多，我不知道大猫有问题。对，那如果没有问题的话，我们就上到这里。